Yay. Okay, so Mr. Kramer's back. It's been a little longer than I was hoping to get this lecture out there for chapter 21. I did receive you guys' outlines, or at least most of them, if not all. And so I wanted to talk about electric fields in a lecture, and then I'm going to move on probably to the standardized practice test. So if you could open your chapter books for me to page 570, your textbooks to page 570, and we'll get started. I'll say a prayer while you guys are finding your textbook and getting it open to page 570. Lord Jesus, you know me. You know that I am passionate about truth and justice. But sometimes my passion for truth and justice gets in the way of me being heard. And I hate it when that happens. My passion is, I wear it out there on my sleeve. I will get to the point of yelling the truth that you would have us believe when I'm faced with someone that is not believing what they should, or not believing the truth, believing a lie. And while that was somewhat beneficial for the prophet John the Baptist, it's not necessarily beneficial for the people I'm trying to help. And so I ask you to give me peace. I ask you to give others peace that have been prevented from hearing me because of my passion for truth and justice. And I ask you to give me a greater compassion for those that are believing lies. That compassion should not mean that I become silent in order not to disturb others, but rather just be heard, to get to the point where I can be heard, to consider the other person more than I do. In your mighty name, Jesus, amen. Okay, so, defining the electric field. This book this chapter 21 is actually called Electric Fields, and in order to measure an electric field, which section 1 is called measuring electric fields, you have to define an electric field, okay? And they exist. This is a demonstration of an electric field. You can see it better when I go dark, but I bet you can see it somewhat here. There is there's a difference in potential between that center pinky purpley looking thing and this glass globe that goes and completes the circuit. There's something on the inside of this glass globe that conducts, and it is, you can see how it's melded here at the bottom of this base. The glass globe is, and then there's this insulator that goes up to that other glass globe on the inside. There's a little much smaller sphere on the inside, and there's a potential difference between the two, and this electric field that is even. Okay, I should say the electric field is even here in this glass container, and I just had an idea that I could draw the electric field effect, and then when we put something on the outside of the glass that contains mass and or a ground, something that goes to ground, you see a greater concentration of electrical current flowing. and that greater concentration diminishes the rest of the current flowing randomly, so that you see that strong arc. Now there's not a strong arc. All of the flow of electricity is random and moving through the gas, and this is probably some sort of a neon gas or some kind of a gas that provides that color when electrons are moving through that gas. And when I put my finger up here, a greater concentration of electrons comes to that spot on the glass because I'm creating a change in the localized charge on the inside of the glass by putting my neutral hand up and touching it. Okay? Does that make sense? So I'm changing the charge locally on the inside of the glass, and that's why the electrical flow is increased towards my fingers, and you can actually feel warmth here being created on the glass because there's resistance to electron flow, and that causes heat. Okay, so let's draw this electric field that we have here. And I have to assume that the inside, the small sphere in the middle of this outer glass sphere is positively charged, and this outside of the sphere is negatively charged. Let's see, is that right? No, because I think electrons are flowing from the sphere to the outside. So that's actually, so the inner sphere is negatively charged and the outer sphere is positively charged. And I think that's how I'm going to draw the electric field, okay? All right, so here we go. Electric fields are drawn in a certain way. All right, the electrons, this is negative, right? And this out here is positive. All right? And so what happens is the electric field is drawn. I want to make sure I get this right, so I'm going to check. I believe the electric field is drawn, away from the positive and toward the negative. So there's this electric field that goes like this. Bam. 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 And the density of these arrows that I am making has to do with the strength of the electric field. All right? The stronger the electric field, the more dense I would draw those arrows from the positive charge to the negative charge. So that's an electric field of this little device that I've turned off already. Okay. So an electric field is defined in your book on page 571. The strength of an electric field. Electric field strength, okay? The strength of an electric field is equal to the force on a positive test charge divided by the strength of the test charge, okay? So there's a big formula for defining an electric field. E is equal to the force on, and this is all one thing, force on Q prime divided by Q prime, okay? So the force on Q prime, that's one thing, F, okay? That doesn't mean F times Q prime. That is the force on Q prime, and that's F, that's a vector, and then you divide that force by Q prime and you have what's known as the strength of the electric field. Okay? So if I were to drop a test charge into an electric field, that test charge would begin to move in the direction of the electric, positive. If I drop a positive test charge into an electric field, it will move in the direction of these arrows. Okay? Does that make sense? It will move in the direction of the arrows. Okay? A positive test charge will move because it has an F associated, it has a force associated with it. Okay? And that force causes the positive test charge to accelerate. Now, this is the definition of an electric field, right there. Okay? And let's talk a little bit more about that concept. So let's talk about Coulomb's law and the electric field. Okay? This is what you get. So if E is equal to the force on the test charge divided by the charge of the test charge, then you get, then that's equal to the force on Q prime times, you separate that out, okay? F on Q divided by Q prime, well, can you see here? If I draw right, no, not right there, here. So F on Q, which is one thing, that's just the force on the test charge divided by Q prime is equal to F on Q prime times 1 over Q prime. Okay? All I did was take 1 over Q prime and put it over here by itself. This is one thing, and this is another thing. So this is true. That's just algebra. Okay? Everybody follow that? F on Q prime divided by Q prime is equal to F on Q prime times 1 over Q prime. Okay? Now, let's talk about Coulomb's law. And let's look at Coulomb's law. Okay? Well, we know that in Coulomb's law, we have F is equal to K times Q1 Q prime, I'm going to say now, divided by the distance squared of things, all right? So we know this is true. So F is equal to this. We know that's true from our last chapter. We've done a lot of mathematics associated with that. This should be something that you're familiar with. Oh, but you can't see what I've written down. I'm sorry. I'm going to turn this over here a little bit and get out of the way. So this is what I wrote down. I wrote down Coulomb's law. Okay? F is equal to K Q1 Q prime divided by D squared. Okay? Now, if I want to know what E is using Coulomb's law, all right, I know that that is equal to K Q1 Q prime divided by D squared times 1 over Q prime. Okay? This is E is equal to F divided by Q prime. All right? Okay? Can you see that? So this is E. So if I'm using Coulomb's law and I define this to be true, the E field strength is equal to the force created on a test charge divided by the test charge. If I define that, then I can also say very quickly that E is equal to K Q1 divided by the distance squared. All right? Because that makes that go away. Okay? So E is equal to KQ1 divided by D squared, the electric field strength at any given point. All right, now let's understand why that's important. I'm going to move over here to this board. Okay? Why is that important? Well, if I have a positive particle in the world, and the E field goes away from the positive particle, okay? And the density of the arrows corresponds to the E field strength. All right? 1, 2, 3, 4, 5, 6, 7 arrows. So that corresponds to the E field strength. Thus, that corresponds to the charge, the magnitude of the positive charge on this particle. Okay? And if I want to know what the E field strength is right here on the surface of the particle, well, I know that E is equal to K times the charge of that particle, charge on that particle, divided by the radius of this particle, right? If I want to know the E field strength on the surface of this particle, okay, radius squared, right? If I want to know what the E field strength is right here, well, I know it's equal to K times the charge on the particle times that radius. Are you following me? So the center of charge is, and the charge is positive, so I know the E field strength at any given place. All right? And that's why you combine Coulomb's law with this definition. Coulomb's law, oh, I lost the power cord. Just a second. So Coulomb's law combined with the definition of an electric field strength, okay, gives us that result. E is equal to K Q1 divided by the distance squared, okay? Are you following me? And the density of the lines, the way we diagram E fields, the density of the lines corresponds to the strength of the E field, okay? So that's kind of sort of 570 and 571. You get, by the way, these are units. These are units of newtons, and that's units of coulombs. So E has units of newtons per coulomb. Okay? I'm sorry, I drew something on the board and I wasn't pointed at it. Newtons per coulomb are the units for E field strength. Okay? That's pretty, I think that's fairly intuitive, given the fact that you have a force divided by a charge, and the charge is in units of coulombs, and the force is in units of newtons. So newtons per coulomb is an E field strength. Okay? All right. And that's what you'd find if you plugged into this formula, right? You still end up with newtons per coulomb, right? Because this is, the K is in units of, let's see, it's in units of newtons per coulomb squared meter squared, right? And so this becomes, when you have KQ1 divided by D squared, so here's a coulomb divided by meters squared, and you end up getting rid of the meter squared and getting rid of the coulomb squared, and it's newtons per coulomb. All right? Oh, again, I didn't show you that while I was doing it. Forgive me. All right. So this is what I just got done doing. Newton meter squared per coulomb squared. I multiply that by coulombs. I get rid of the coulomb squared in the denominator and get rid of that coulomb. And then I divide this by meter squared, and I get newtons per coulomb are left. That's what that boils down to, is a newton per coulomb. Newton per coulomb. Okay? Newton per coulomb. Newton per coulomb. Okay? Good. So we talked a little bit about the units there. we're understanding a little bit more about what an electric field is, how it's defined. It's the force on a test charge divided by the test charge. Or electric field strength is, when you combine this definition with Coulomb's law, you find out that the electric field strength at any point near a particle with a charge Q1 is KQ1 divided by the distance from the center of gravity or center of charge on that object. Okay? The electric field strength at any given point. So it's easy to calculate the electric field strength of one particle. It starts to get a little more complicated when you're talking about more than one particle being in an electric field. Okay, so modeling the electric field. I've now moved on to page 574, okay, in your textbook. So we talked about this positive sphere and this negative sphere causing an E field that looks something like this, okay? Here we talked about a positive sphere where the arrows go away from a positive sphere. I'll give you one more little example, and that is a negative particle. And the E field arrows come toward the negative, okay? And that's because the E field is defined with a positive test charge, okay? And the motion of a positive test charge is towards the minus. I'm going to make this one more dense. This is negatively charged to a greater extent than this is positively charged. If this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 versus 7. Okay? So the density of the lines is also used to describe the electric field strength. Okay? The relative density of the lines. Now, let's talk about two different particles. And let's here, this is kind of sort of one geometry. Let's talk about this positive and this negative charge being next to each other. Okay? So what do? You actually combine these lines. So this line, is going to go to there. And this line is going to go to there. And this line is going to go to there. Etc., etc., etc. Okay? Bam. I don't need an arrow there. Okay? But you could put arrows here. It doesn't hurt. Okay? Let's put this arrow. This arrow is going to come around here and hook on there. This arrow is going to come around here and hook on there. Okay? So, if these are next to each other, this is what the E field looks like in diagram form. Okay? And this, because this is a higher E field, this adds to there's multiple lines here that don't necessarily come back to here. Okay? And so there's lines that come from nowhere because this is charged to a greater extent than the positive charge. Okay? So anyway, I'm looking on page 575 and I'm looking at figure, what's this figure? Oh, it's on page 575. There's a positive particle and a negative particle, and showing the E field going from the positive particle to the negative particle. The electric field lines of two equal and unlike charges form continuous lines from the positive charge to the negative charge. The vector of point P, okay, shows the direction of the electric field. So everybody see that? So you have tangent lines. Where the lines are closest, a charged particle would experience the most force. Where the lines are closest, a charged particle would experience the most force. Okay? That makes sense. So, anyway, you talk about, so the E field strength at point P would be off in that vector direction. Kind of important to understand the tangent line of the E field. You see this right here? The E field strength can be calculated by either measurement or by, the distance from here. There's a vector that goes away from that particle, and here there's a vector that goes towards that particle, and the addition of those two vectors is that vector right there. Okay? Does that make sense, everybody? It happens to be tangent to a properly drawn E field line. You know what I'm saying? But this is the addition of the vector caused by this particle in that direction and the vector caused by this particle in this direction. Okay? Everybody follow that? All right. And you can see there an example of the two positive, how the E field actually repels. Those two particles are repelling each other, and that's why the E field looks like it does here with the two particles repelling each other, right? Okay. And it's interesting how they made these diagrams. They're bringing in a point charge to rice sitting in a petri dish, and they're making the rice line up with the E field lines, if you will. Okay, and then they're just drawing the E field in the other schematic there, the other part of the schematic. Okay. So another example. This is not a Van der Graaf machine. This guy does not shock you when you touch it, or it doesn't create a flow of electrons to you per se. Okay. It does flow electrons from the middle sphere to the outer sphere. This Van der Graaf machine actually creates a positive charge on this dome because it is being rubbed by something down here. This ribbon is being made to be positively charged and going up and rubbing something else that's in contact with this sphere. So it's pulling electrons away from this sphere because of the material of construction of this belt so it's pulling electrons away, and down here it's discharging electrons, and then going back up and pulling electrons and discharging electrons. And you can get to a very high voltage with this Van der Graaf generator, such that when somebody touches it, their hair is all the same charge, and then it expands and opens up. We talked about that during the last chapter discussion. So that's what a Van der Graaf generator does. And then there's energy and electric potential. They talk about here in section 2, applications of electric fields. So now I'm on page 577. Okay? Applications of an electric field. So there's actually potential energy associated with a position in an electric field. The electric potential difference. Okay? So there's a electrical potential energy associated with where an object is in an electric field. I always have to refamiliarize myself with this particular concept because it might not be intuitive for everybody. So far, everything we've talked about is pretty intuitive, right? We know, we're familiar with Coulomb's law, and we know that he came up with Coulomb's law because of observations that he made. So when we define a test charge as the force on an E field as in newtons per coulomb, the force on a test charge divided by the test charge's charge, and we plug it into Coulomb's law, what we find out is E is equal to KQ1, the charge on an object nearby, creating an E field, divided by the distance from the object. Okay? So we know this is true. That's pretty intuitive, using Coulomb's law, and then using the definition of an E field right here. Okay? So that's pretty intuitive, right? And then we talked about how you diagram an E field, right? Defining an E field. So we did some diagramming. We talked about the application of a Van der Graaf machine. And we talked about the application of this device right here and how that works. So a Van der Graaf generator creates a positive charge on its sphere because of its material of construction and the way it's fabricated, and there's a motor that makes that belt go up and down and continuously charge the sphere, right? When somebody touches the sphere, what happens? It's positively charged. It needs electrons. So it will actually take electrons from the person touching the Van der Graaf machine until the voltage between the Van der Graaf machine and the person is the same. Okay? So the electrons are pulled from the person touching the Van der Graaf machine, creating a positive charge on the person. The average between the Van der Graaf machine initially and the person, it brings a neutrality between the person and the Van der Graaf machine when you touch it, and therefore the person becomes positively charged. They're starved for electrons, okay? And the Van der Graaf machine has a wire to ground at the base of it. This is going to ground at the base. So electrons that are coming from this stainless steel sphere are going off to ground because this is going by a magnet, okay? This belt is actually being driven by a pulley and a motor past a magnet, and the electrons are being driven to ground here. And so you end up with a positive charge here at the top of the Van der Graaf machine. Okay? God bless. So, now we're talking about the potential energy that exists in an electric field. Okay? So, just as gravity's potential energy changes with height, mgh, right, on the Earth, there is and a ball changes its height from high above the Earth to just barely above the Earth, you would say that it lost potential energy and gained kinetic energy as it fell, right? So just as gravitational potential energy exists between two masses, electric potential energy exists between two charged objects, okay? And if you have two positively charged objects and you move them real close together, then they are really wanting to fly apart bad. And so the potential energy that exists between two positively charged objects is greatest when the two positively charged objects are real close together. For example, the nuclei of a helium atom, okay? And or pushing two north poles of two magnets together, okay? So anyway, the electric potential energy increases as the two positively charged objects come close to each other. Now, if you move a positively charged object and a negatively charged object away from each other, now you're increasing the potential energy, right? Okay, so because if you let go of one, it will accelerate toward the opposite charge, okay? So electric potential energy increases if as you get further away, when you have a positive and a negative charge interaction, and electrical potential energy increases when you move them closer together if they're both the same charge. Are you following that? It's a concept that you want to get comfortable with, okay? And let's talk about it. In an example, I'm looking on page 578, and you've got figure 9 here, okay? And what they're saying is that this is a negative charge, this blue ball, and this pink ball is a positive charge. And you're going to move from point A to point B. And so you're going to have to force this positive charge away from that electrical charge. The force on the charge exists, okay? And here you have a low potential energy, all right? You're doing work on moving. This is force times that distance. You're doing work that is represented by this gold bar. And then the final potential energy is the original potential energy plus the work, or right here. This bar is the new potential energy given the new location, okay? So there's a low, it's called, now we're going to switch terms. We're going to go from a low potential energy plus work plus a high potential energy, or going to a high potential energy, and they're calling it the voltage, okay? The voltage, right? And so if you read that paragraph, electric potential difference, we're talking about the electric potential difference from point A to point B. The electrical potential difference between point A and point B is this work that you had to do in order to move it from point A to point B. Okay? So, electric potential difference is the ratio of the work needed to move a charge to the magnitude of that charge. Okay? So, when you talk about electrical potential difference, they talk about a delta V. Okay? And that's equivalent to the work to move the test charge divided by the test charge. Okay? And that's the same thing as talking about joules per Coulomb, or a volt. A volt is a joule per Coulomb. Okay? So, let me write that on the board for you. I'm going to erase this fancy thing and write it on the board right here. All right? Now, let's review. When I move, here's this negative point charge, all right? And here's this positive test charge. And I'm going to move it from this distance away to this distance away. So I'm going to move this positive test charge from there to there, all right? And I've given it more potential energy when I move it. Okay, now it has more potential energy because these are opposite charges. I moved it further away. You have to get used to doing that intuitive analysis. So this has greater potential energy than this one. This has less potential energy. Okay? And I had to do work to move it from here to there. I had to do work to pull that away. Force times distance. Now obviously the force required to pull it away diminishes as I pull it away. Right? You follow that? So because the force is equal to the electric field times divided by the test charge. Let's see if I can help you make sense of that. We know that E is equal to F divided by Q, okay? But that force is equal to this. So as you move away from the point charge, your electrical force diminishes by the square of the distance, okay? So your force is changing over this distance away from there. If this stays in place, your force is changing with the distance. And then you multiply, so this is the integral. So here, this is what this looks like. The force divided, and the distance, if you plotted the force and the distance, what you get is, let's see, it would do something like this. Okay? Does that make sense? And the work that's done is the area under this curve. Force times distance for each of those different forces. Okay? So it's the area under that curve is this force times distance. So that force keeps changing with the distance, and then you multiply it by the distance moved, etc. And this is the concept of integration. The area under the curve. You have to integrate the force distance curve in order to understand the work. Okay? I just wanted to point that out. I hope that made sense to you. Now, here we go. We know that you do work in moving the point charge away from the object. Sometimes it's easy, sometimes you get work out when you move like if this were a positive and this is positive and you go from here to there, sometimes this is work out instead of work in. All right? But anyway, so there is and then, matter of fact, is that shown? Yeah, you go from further away to closer away is what's shown there. If you on page 578, the second figure at the top, that's not showing you two like charges, but rather it's showing you going from point B to point A, and the fact that you can get work out of such a situation. Okay. All right. So they talk about the change in electrical potential from this place to this place, okay? So the potential energy is greater, and what they're saying is that what they're saying is the potential energy is equal to V, voltage, okay? Or delta V. Potential energy is equal to the change in voltage. And that would be the potential energy here, this change in this voltage is the potential energy required to bring this particle from infinity away to this position. Boy. Wow. From infinity away to that position is the potential energy of that position. All right? Or you can talk about a change in potential energy. Okay? So anyway, it's an interesting concept. It's spelled out in the book. I'm just gonna at this point, I'd like to be able to explain it better, but I'm just gonna give you this definition that the change in potential energy is equal to the work required divided by the test charge. Okay? Electric potential difference is the ratio of the work needed to move a charge to the magnitude of that charge. The ratio. Okay? And that's considered a volt. And you guys can read your textbooks and try to get your head wrapped around it even better than I'm maybe even explaining it. But that is the concept of voltage. That's why batteries with chemical potential energy, a driving force for moving electrons from the negative side of the battery to the positive side of the battery, if you give it a conductor to move it in. That's a voltage. There's a voltage potential difference, okay, to move electrons. Electrons being the test charge at this point when we talk about electric circuits and things like that, okay? It's electrons that move. It's never protons that move in an electric circuit. But we'll talk about, hopefully we'll have a chance to talk about that next week, okay? As a matter of fact, I better go ahead and talk a little bit about where we're headed next week. Electric current is the next chapter. So we're going to talk about electric current, and we're going to get that far. And then, because they've shortened the school year on me, I'm not going to have a chance to do chapters 23 and 24. Okay? I apologize for running out of time. But hopefully we'll get through the standardized practice test for chapter 21 and the standardized practice test for chapter 22 over the next week and a day or so. And I will work toward that. And I need you guys then to do the chapter 22 outline. And I'll get that written down or maybe I think I've already said that on Google Classroom. Chapter 22 outline is probably due about now, I think I said last week. Okay? So anyway, I'm going to get through the standardized practice test for chapter 21 in my next lecture, and then we're going to move on to chapter 22. Now, there's something I want you to understand. When we define this change in voltage equals work divided by Q prime, you can, and we combine that by with a couple of other things. We find the electric potential in a uniform field. That when we talk about a uniform field of electric potential, what we're talking about is this kind of a configuration. Okay? Because these two spherical surfaces are parallel everywhere, we have a uniform electric field inside these two, inside this glass sphere, in between the inner glass sphere and the outer glass sphere. We have a uniform electrical field, okay? The electrical field strength near the center of that ball is the same as the electrical field strength out here near the glass, okay? That is a phenomenon of uniform electric fields. What happens? What do you have if you have a plate rather than a particle that operates spherically with its electric field? You have two plates. This is a capacitor, by the way, what I'm about to draw for you. All right? So in the special case of two parallel plates where there's a voltage across these plates, what you end up with is an electric field that is constant everywhere, from the inside of this plate to that plate. It doesn't get stronger as this from between these two plates. It gets a little bit funny out here on the edge, right? Because it's the edge. But in the midst of these two plates, it's uniform. The electric field is uniform in strength. I tried to draw these arrows equally apart, but I goofed a little bit. So bear with me, or forgive me for not drawing those arrows perfectly at the same density, okay? So this is a positively charged plate, so the arrows go toward the negative plate, okay? And inside here, whether you're at this point, or at this point, or at this point, or at this point, or whatever point you're at, in between these two plates, the electrical field force is not changing, okay? And so you can determine the electrical field strength by seeing how long it takes a test charge to travel from this plate to this plate, okay? And what happens is when you do something that particular math, you know the definition of an E field, okay? The force on a test charge divided by the charge on the test charge. That's the definition of an E field strength, okay? And you know that delta V is equal to, let's see, that's equal to the work, right? Work divided by Q prime. All right? So you know those two formulas, and we've derived those intuitively. This is what you find out when you use these two equations, okay? You find out that let's see if we can do it. So what this means, this is equal to FD, by the way, this is D, this gap distance, D. F times D, since the force everywhere is the same, so in this special case, you don't have force changing with distance, you just have force, not changing with distance, times this distance, okay, is equal, divided by Q prime. All right, are you following that? Now, so what is delta V equal to in terms of E? Okay, so we know this is true for a capacitor, exactly, where this is D, and the force is the force, and the test charge, okay? And this is true inside a capacitor, okay? So we know that this potential difference, here's the positive side and the negative side, since there's a we know this happens to be delta V, all right? And so we know that this is delta V between those two plates. And that's FD divided by Q prime. But we know that F over Q prime is equal to E, right? So we're going to plug in E for F over Q prime. So we know that delta V is equal to ED. And this is true for capacitors, where you have parallel plates with the voltage potential between them, and the distance between them is D, then the voltage potential across the plate is equal to the electric field strength times D. This is important for answering many questions about electricity and stuff like that. Were you guys able to see that? Right? Okay? So this is a capacitor, and this is true for a capacitor, okay? Parallel plates with a voltage potential from one plate to another, and the field strength, it's equal to, so the change in potential is equal to the field strength between the plates times the distance between the plates. And that's for a special case of a capacitor, okay? a uniform field of electricity. Okay? And then there's Milliken's oil drop experiment discussed in this chapter. This is fascinating. I find Milliken's oil drop experiment just fascinating. Milliken was able to figure out the charge on a, what does he call it? The something charge, elementary charge. Milliken is able to figure out the elementary charge to 3 significant digits using his famous oil drop apparatus. And of course the elementary charge is either the positive charge on a proton or the negative charge on an electron. And he did that because he set up a known voltage potential here across these 2 parallel plates where the E field is constant and the force on a test charge is constant. And he would drop an oil drop through this upper plate by atomizing a mist of oil drops here. And an oil drop would fall through this plate, and then he would adjust this voltage potential so that the oil drop floated. Okay? And he noticed that the various Q primes that he got, okay, E is equal to delta V is equal to ED. Well, D wasn't changing between the 2 plates, right? The distance between these 2 plates was not changing, okay? And so, and he knew what the delta V was, so he knew what the E was in between these 2 plates. And he actually figured out the elementary charge by he noticed that the voltage potential had to change correspondingly depending on how many electrons were either missing from neutral or increased from neutral. Okay? And so he noticed that, oh, look, these voltages that I need to float these oil drops correspond to an elementary charge. He noticed there was a finite amount of charge increments on each oil drop. And because he noted, and he didn't know electrons existed or protons existed all by themselves, and so he was way ahead of himself figuring out what the elementary charge was as an increment of the elementary charge on oil drops. And he actually figured out the charge on an electron and the charge on a proton because of this oil drop experiment. And I really do, I invite you to read about Milliken's oil drop experiment and become familiar with that, how he did that. It is amazing to me how he did that. That was a great experiment and a great thing, okay? And now we talk about electric fields near conductors. There's irregular surfaces and things like that. But what you want to know about this is a conductor distributes the electric charge evenly on its surface, okay? So if you have a funny shaped surface, what you're going to find is that there's a little bit more negative charge out here on the tip because there's greater surface area on the on this pointy part of the egg on that end of the egg. Okay, so if you're close to this egg-shaped object, what you're going to find out is that you're going to find a stronger electric field here at this point than you would over here at this surface, because while the electrons are spread out evenly on the surface, there are more electrons at this end of the egg than at this end of the egg because they're distributed evenly. And there's more surface area at this cone-shaped end instead of the spherical end. You understand? So So that's kind of sort of, you can have an irregular surface that creates differences. Obviously, a hollow sphere, if you negatively charge the hollow sphere, then the negative charge will all be on the surface, not inside. Inside the sphere, if you have a hollow sphere, inside the inside surface of the sphere will be neutral. And the outside surface of the sphere will have a negative charge, because the negative charge is repelling other localized negative charge, and so it's going to be on the outside surface, and it will be, and the inside of the surface will not have any negative charge. So even though you're talking about a hollow sphere, the E field around a hollow sphere is a direct result of the excess charge on the outside of the hollow sphere. I think the guy Gauss, G-A-U-S-S, figured that out, and that is that the charges reside on the outside only. It doesn't become positive on the inside of the sphere either. It just is just neutral on the inside of the sphere of a conductor, and all of the excess charge is on the outside, okay, of a hollow sphere. All right? So that's true whether you have a hollow sphere or whether you have a solid sphere. There is no excess charge on the inside of a steel ball. Okay? There is no excess charge on the inside of a hollow steel ball. All the excess charge is on the outside of a conductor. Okay? And then when something doesn't conduct, like a rubber balloon, you can actually create a localized charge in the vicinity of an insulator, something that's an insulator normally, something that doesn't readily conduct electrons. There you can have a local charge because of rubbing electrons off of that material, and then and it not moving the excess positive charge left on the rubber. The electrons don't move in to make it uniform everywhere. Okay, so you can't actually have localized charge in an insulator if you create it. Okay. So then one more definition looks like given in this book that we want to somewhat be aware of, and that is the concept of capacitance. We talked about the fact that a capacitor has a uniform E field. We know that delta V is equal to ED inside a capacitor. Okay, this potential, delta V, that is easily measured with a voltmeter. Okay, and this distance is easily measured with a ruler. And so we can figure out what the electric field strength is inside a capacitor. Okay? Just so happens it's handy that way if you want to know. And now capacitance. So in order for me to talk about capacitance with some level of understanding, I'm going to have to read this to you, okay? Suppose you connect the positive terminal of a 1 volt power source to one of the conducting plates of a capacitor, and connect the negative terminal of that power source to the other plate of that capacitor. What happens? The power source would produce a potential difference of delta V of 1 volt between the two plates. Okay? So now what we're saying is this delta V is equal to 1 volt. Okay? And this would result in a net positive charge of plus Q on one plate and a net negative charge of equal magnitude minus Q on the other plate. So that's intuitive. So what you're doing is you're creating a charge on the metal, on the surface of the metal plate, okay, when you hook up this voltage to the two metal plates. Now suppose that you increase the voltage of the power source. What happens to the amount of net charge on each plate? Well, it goes both up and down accordingly, okay? Figure 16. Oh, this down here. Figure 16 shows the results of an experiment in which the experimenter increases the potential difference across the capacitor's plates from 0 volts to 12 volts. Okay, so you see the potential difference between the plates from 0 to 12 on the x-axis. And then you talk about, notice that Q, the charge on each plate, okay, is given over here. There's a data table, and then they plot that, and it's a straight line, okay? So what they're saying is, because it's a straight line, because the graph of potential difference versus charge is a straight line graph, okay, they call the resulting charge divided by delta V, the slope of this line, okay, dy versus dx, delta y, rise over run, is equal to capacitance, okay? And that's how they define capacitance. So when you see a capacitor is so-and-so coulombs per volt, okay, when you see that on the side of a capacitor, you know that it would be a straight line graph of this Q divided by delta V. Okay, you see what I'm getting at? So a capacitor, as you plot charge versus voltage on a capacitor, all right, and each capacitor's, the geometry of each capacitor creates a different charge versus voltage graph. All right, the geometry, the square feet, all right, or let's call it square meters. The meters squared of this plate and the meters squared of this plate and the distance between them creates a different charge given a certain voltage. Okay, and so this capacitance, the slope of this line, or change in Q, or I'm sorry, not change in Q, but just Q divided by V, because it starts at 0, 0. Okay, so the capacitance is equal to Q divided by V. It always starts at 0, 0. If there's no voltage, there's no charge between the two plates, and the capacitance is 0. Okay, I'm sorry. That's not right. The geometry of the capacitor drives what the capacitance is. If you put a voltage on a capacitor and can determine the charge, there's an average charge of 0 between the two plates, but there's a positive charge and a negative charge, and the average is 0. So you determine the magnitude of the charge given the voltage, then you know what the capacitance of the capacitor is. And capacitance in a capacitor actually is stored energy, okay? You have to, in order, when you hook up this power supply onto the two plates of the capacitor, you're actually charge up the capacitor. And now there's energy, electrical field strength energy in the capacitor. And when you disconnect this power supply from a charged up capacitor, it doesn't discharge unless you hook up a wire between this plate and this plate again, and then it will discharge one plate to the other. You'll get current to flow through that wire. Okay, we're going to talk more about that in the next chapter too, but I wanted you to be aware of that. The driving force that what makes current in a conductor. Okay, electrons will actually flow from a negatively charged plate to a positively charged plate if they're hooked up with wires. Okay, and so when you hook a battery up to a capacitor, it charges the capacitor up. Electrical energy goes into the capacitor to the extent that the capacitor can hold electrical energy given its geometry. Okay, and capacitance is defined as the charge on the magnitude of the positive or negative charge on a plate, on either plate, the absolute value that's given divided by the voltage required to make that charge. Does that make sense? I hope. Okay, that's how they defined it. It happens to be the slope of the line between the charge that's created by the voltage. That's the capacitance of the capacitor. Okay? And the charge that's created is a direct result of the voltage between the two plates, and that's how they define capacitance. Okay? What else? Oh, the farad. That's a farad, by the way. They talk about coulombs per volt is a farad. Okay? 1 farad is 1 coulomb per volt. The units of capacitance, a farad. Okay? So now we are ready for the standardized practice test given chapter 21. If you feel like emailing me a question or 2 or 3 or whatever, if I said something that didn't make sense to you, after studying a little bit with your textbook, you still can't figure it out, feel free to email me. Feel free. I will be glad to answer your questions. And now, the next time you see a video from me, we're going to go over the standardized test practice for chapter 21, and then we'll move on to chapter 22 lecture and the standardized test practice for chapter 22. Okay? And that'll be the extent of our physics class for this year. And I got to just say one last thing. I loved having you guys in class this year. It was awesome. You're a great group of students, and you can conquer the world if you want to. Let me know if I can be of any assistance. I know I act kind of goofy sometimes. As a matter of fact, let me act goofy with you one last time here in this lecture. Okay? Have you guys seen this over here? This is my drum set up in room 320 over there. I have a chair on that table because I sometimes put my Chromebook over there to video my playing the drums. And I'm not going to do it now. I'm just going to go over there and play the drums a little bit just to give you a little taste of how much I love you. Because it's pretty kooky. I'm willing to be kooky for you guys' sake. Okay, hello? Not on. Oh, did I leave it on? No? I didn't turn the mic on. Hello? All right, you guys. I can be a little kooky and still know physics and hopefully help you guys to learn physics. We went over a lot today. First of all, the definition of an E-field strength is the force on a charged particle divided by the charge of the charged particle. E-field strength. The force on a charged particle divided by the charge on that charged particle. Woo! And then E-field strength, when you combine that with Coulomb's law, you find out that an E-field strength is not only equal to the force of divided by the charge on the charged particle, but you find out that it's equal to Coulomb's constant times the charge on the particle that's creating the E field divided by the distance from that particle squared. Woo! Divided by d squared. So if you have a single particle, let's say it's positively charged, you can very quickly calculate the E field strength anywhere in the E field. Okay? And or you could be given the force that is placed on a test charge and the charge on a test charge and calculate the E field. Right? So these things are, we'll experience the use of these formulas when we do the standardized practice test. What else did we learn? Well, let's see. We learned that delta V, the change in potential of a particle from one position to another, the change in that voltage, if you will, is equal to the work to move that particle from one place to another. So the change in potential from one place to another is equal to the work required, force times distance, and we know that that work is equal to force times distance divided by the charge. So the work required to move a particle divided by the particle's charge is equal to the change in potential of that charge. Da, 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 da. All right, so that's another big one. And so delta V is equal to W divided by Q. And we also learned that for in between two parallel plates where the difference in charge between each plate is the same, everywhere inside those two parallel plates, the electric field strength is the same. And so when we're talking about capacitors, we know that E is equal to F divided by Q. E is equal to F divided by Q for capacitors. And we solved for that. And we also learned about how to determine the capacitance of a given conductor field geometry, okay? And the capacitance is equal to Q divided by delta V. Da, 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 da. And that's measured in farads. A farad is a Coulomb per volt. Delta V is also equal to ED in a capacitor because the electric field strength that happens to be the same everywhere in the capacitor, okay? And we observe that when we have two parallel plates like in Milliken's oil drop experiment and you have a drop of oil floating there between the plates, we can see that the electric field strength is the same from one plate to the other because the acceleration of the drop remains the same. Yeah. The acceleration of the drop. Let me think about that for another second. The force on the test charge doesn't change in an oil drop experiment. So an oil drop will fall at a constant rate from the once it enters the chamber between the two plates to when it lands on the plate on the other side. So that means there's no acceleration. So that means, I'm not sure. I'm talking off the top of my head, and I'm not sure if I'm telling you the truth. But know that it's a scientific fact through observation that the E field strength does not change between two charged parallel plates that are in close proximity to comes and give you a fun, silly, room 320, jazz up the lecture thing. God bless. You guys are awesome. Unfathomably precious.